Hello, everybody. I'm Douglas. This is Austin, Cooper, Stephen, Rahul, and Robert. Our team name is LTC Dynamics, and our project was to design an LTC advanced motor drive. So what is an LTC? So let's say you have a transformer that's part of a power grid. The power that transformer needs to output is going to vary depending on the time of day. To be able to meet the varying power needs, the transformer will have a system called a load tap changer, LTC. What the LTC does is that it reads the power demand that the transformer needs to output, and then depending on whether it needs to increase or decrease, it will change the number of turns in the coil that's inside the transformer to meet the desired power needs. Our corporate sponsor, SPX Transformer Solutions, they have an LTC system as one of their products, and their system uses electromechanical components and an AC motor to drive the system. They asked us for our project to make a system that uses a servo motor and a digital logic controller to drive the system. The reason why they wanted that is because it's going to have less components, which means less maintenance, and as well as there's other features that we can add, like having a user interface and event logs and alarm logs. There's some metrics that we had to meet for this project. It needed to have the correct amount of torque, which was about 110 foot-pounds. It needed to be able to monitor all the positions that the LTC will have, which is going to be a total of 33 positions. We did that by having encoders and other sensors. It needed to have, it needed to be able to perform 1 million operations without maintenance, have an operating temperature of -40 to 50 C, and our prototype needed to be less than $50,000. I'm going to pass it down to Cooper.
So to start off for our system overview, there's three main components that we'd like to go through right now. The first is the controller. We initially thought we could use a microcontroller to facilitate monitoring of the system, as well as sending signals to the motor drive to send out to the motor to facilitate a raise or lower on the tap. But then after talking with our corporate sponsors, we decided that a PLC would be the better way to go with that. It's more robust and more modular. So to start out, for a raise signal, the controller will receive a raise signal from voltage relays, and it will then via a RS-232 serial connection to the motor drive, send a signal to the motor drive, which will then send a signal to the three-phase AC servo motor, which will rotate a shaft that will go up into the taps or raise or lower the taps. Once it has done a full 360 rotation in around 2.5 seconds, the absolute encoder will send back a position to the motor drive, which will then send back a signal to the controller, telling it has done a full raise or lower. It will raise or lower. It will then look at three signals coming from the tap that will indicate charge signals from vacuum bottles inside the tap. And it'll also monitor another encoder that's on the shaft at the tap to look at position. Once it has compared all three of these signals, it will determine if alarm conditions are met. One could be that the vacuum bottles did not discharge properly, and so it needs to send out an alarm for that. Another could possibly be that the shaft encoder and the servo encoder do not agree with each other, so then it will output another alarm to one of our HMI panels that's connected via Ethernet. And that's kind of the basic overview of the system. Just as another note, the controller should be able to store at least a year's worth of different kinds of operations, how many taps and so forth were done daily, weekly, monthly, and that sort of thing. And it will also facilitate user actual manual lower and raise. So that's the real system.
I just had a question about your goals and metrics. They don't seem to be objective enough to really easily show that you've met those in the next semester. When you be able to perform 1 million operations, are you going to be able to test to that level, and what does that mean, perform? That's kind of a loose term in engineering terms.
So for performance, it means an actual tap change, so having the 360 rotation of the shaft. Because a lot of these components are really expensive and it's gonna be based off of our corporate sponsor, whether or not they wanna go with a certain component or another component. It's really looking at the data sheets and saying, is this gonna be a robust enough component to be able to handle this?
Okay, are you going to be able to test to that level for your next semester?
Next semester is when we're gonna be testing. I think we're gonna, at best, just try to see how many operations it can do, depending on the timing of it and all that, because we still have to wait for the parts to be ordered.
Okay, if you're not gonna take the data, then don't make that part of your objective. You need to have an objective that you're actually going to meet in the time frame that you have allowed.
How are you going to calibrate this motor system with the encoder and the servo motor? Do you have a plan for that? So you know what revolution is a revolution, so you can make a temperature?
I don't think, from our understanding, I think we're using, so we're gonna be using an absolute encoder. We don't have like a set plan yet for that. We are, because the corporate sponsor, depending because on time and whatnot, we're in scheduling. We're gonna be doing a failure analysis in the next couple of weeks to figure out what exactly, and other failures as well, like if there's like a power surge or anything else like that, and that's probably gonna be one of the things we have to talk about as well.
Do you have a preliminary bill of materials costing to tell you if you're gonna be close to the 50,000?
Yes, we do, and we can't go into the specifics, like how much exactly, but it's below that. It's well below that.
What exactly is the objective?
The objective, so the system they have now is electromechanical and it uses an AC motor rather than a servo motor. So they wanted to have a servo motor and a digital logic controller to be driving the system instead. They want, like I said, it's going to be less components, so they don't want to have quite as much maintenance, less parts. If something does break, less parts to replace. And they also want to have like a user interface that has events and all, event logs.
So you're just controlling a servo motor with feedback?
Yes.